40 is a problem that has two line charges, infinite line charges oriented along the x-axis as shown like this. So there's a line charge here, and a distance d away on the x-axis is another line charge. So each one is sort of symmetrically placed around the y-axis at a distance of d over 2 there, and a distance of d over 2 right there. What the problem is asking for then is what is the net electric field at a point y above the midpoint between the two line segments. So these are infinite lines of charge here. They look like point charges the way I've drawn them, but they're not. They actually extend all the way back into the paper that way and into the paper that way, an infinite distance, and out in front of the paper an infinite distance, forming two infinite line charges as stated here. So the only thing we know to start the problem is that the electric field due to an infinite line, this is a result from class, is 2k lambda over r. Now in this expression here, lambda is the charge density on the infinite line of charge, and r is the distance away from it. 2 and k are the usual things, k 9 times 10 to the 9th, the usual constant there. So what we would do in a problem like this then is say, okay, it's another electric field superposition problem. Here's the point right there, and we'd like to know what the electric field is. Well, this positive line charge will have an electric field emanating away from it in all directions. Of course, one of the electric field lines will go right through that point there. We'll call it EL, E due to the left, infinite line charge. This one will also have an electric field going through this point, and I'll sort of draw it like that, and I'll label it ER, E sub right. So at this point, there are two electric field lines, each from each infinite line charge going through the point labeled ER and EL. Now, if you look carefully at the problem, there's immediately some symmetry arguments you can apply to make your work a bit easier here in finding the total electric field at this point, which is what the problem is asking for. In particular, if I just start drawing the x and y components of these two electric fields, here's ERX and ERY. Likewise, there's an x component over here. I can call it ELX, and this one right here can be called ELY. So we can have the two components in there. You can look at it sort of immediately, given that the charge density on the left and right infinite line segments are the same. You can look at these two components here and see that they cancel. So indeed, at this point right here, EX at this point is going to be 0. There's going to be no net electric field at this point along the x direction. The y direction is a different matter, though. In fact, ELY and ERY both point upwards like that, so there will be a net electric field in the y direction at this point. So I can sort of start by saying E total then is basically going to be ELY plus ERY, the left and right contributions there. I can proceed to compute this a bit here. In particular, I can write that E total here is going to be EL. Now I need some sort of trig function to project the left's electric field onto the y-axis. And if I look carefully at my figure here, I'll note that if this is an angle theta right in here, then this is going to be an angle theta right in here, and that's going to be an angle theta right in there. So I do have some angles I can put on those right triangles that involve my components of the electric fields there. And if I look carefully, I'm looking for the y component, which is going to be this one right here, and it looks like the opposite side. So this is going to be a sine function right here, a sine of theta right there, and likewise for the other one, it'll be E right times the sine of its theta. Because over here, here's the right electric field vector, here's its y component, involves a sine. In this other right triangle, here's the electric field due to the left line charge, here's the angle, there's its y component, involves a sine also because it's opposite to the angle in there. So it looks all good, and we have it in there. So what we can do next is just fill in the electric field magnitude for the infinite line of charge now. We'll get something like E total then is 2k lambda over r times the sine of theta plus 2k lambda over r times the sine of theta. Since everything's looking the same between the left and right line charges, the distance from the field point to the line in question is the same, the r is the same there, the r is the same there, the charge density is the same. We can go ahead and combine these two things here to get that the total electric field then is going to be 4k lambda over r times the sine of theta. So we're doing just fine so far. This might have gotten cut off just a second ago here, but I was pointing at these two r's here. This r is this distance, which is the same as this r, which is this distance right here. So it looks like we're all going okay. We'd like to get rid of the sine now in terms of something into the problem there. So if I look very carefully back at my right triangles, I can see that the sine of this angle here is y, the height of the field point, divided by the hypotenuse here. So I can sort of write over here that the sine of theta looks like it's going to be y over r. And I can fill that in down here. So I get that my total electric field then is going to be something like 4 lambda k over r times y over r for my sine projection in there. Just a couple more steps to get the problem to work out here. The total electric field then is going to be 4 lambda k y over r squared. Now I'm just in the position of needing r squared. And if I look very carefully, r squared then is either this distance or this distance, which can just be found using Pythagorean theorem. So if I look carefully here, this side right here is basically going to be r squared plus d over 2, that quantity squared. Pythagorean theorem. This is one leg, this is the other leg, d over 2. There's the right angle in there. So I can just fill it in for my r squared. I think I'll be just right on top of the answer. The total electric field then is 4 lambda ky over r squared, which is y squared plus d squared over 4. And to make it look like the answer in the book, all I have to do is multiply the top and bottom by 4 just to work on the denominator a bit. And if I do that, I get the total electric field is 16 lambda ky divided by the 4y squared plus d squared. And this would be the answer then. This is the electric field magnitude at a distance y above the perpendicular bisector between two positively charged infinite line charges with charge density lambda. There's your result.